The cold English morning of February 12, 1944, wrapped around the airfield at Molesworth like a shroud. Staff Sergeant James "Jimmy" Donovan stood beneath the massive silver belly of a B-17G Flying Fortress, his breath forming white clouds in the pre-dawn darkness. The bomber, christened Lucky Strike by her crew, towered above him, her 4 Wright Cyclone engines silent for now, but within hours they would be screaming over Germany. Jimmy wasn't like the other crew chiefs. While they followed the technical orders to the letter, checking off items on their inspection lists with mechanical precision, Jimmy listened. He listened to the engines. He felt the vibrations. He understood the machines in a way that went beyond the manuals distributed by Boeing and the Army Air Forces. This morning, something was different. The temperature had dropped to near freezing, and Jimmy knew what that meant. In just a few hours, at 25,000 feet over occupied Europe, the temperature would plummet to 60 degrees below zero. At that altitude, with that cold, machines became unpredictable. Metal contracted, oil thickened, and the turbochargers, those critical components that allowed the B-17 to climb high enough to escape the worst of the anti-aircraft fire, they became temperamental. The turbocharger. Most people who hear about World War II bombers never really understand what made the B-17 Flying Fortress capable of its mission. They hear about the 13 machine guns, the armor plating, the ability to absorb tremendous punishment and still bring crews home. But the real secret, the technological marvel that made high-altitude precision bombing possible, was the General Electric turbo supercharger mounted beneath each of the bomber's 4 engines. Before we continue with Jimmy's story, we need to understand what he was working with. The principle behind the turbocharger was elegant in its simplicity, yet revolutionary in its application. At sea level, the Earth's atmosphere presses down with considerable force, packing oxygen molecules tightly together. An engine at sea level gulps this dense, oxygen-rich air and burns it with fuel to create power. But climb to 25,000 feet, and the air becomes thin, rarefied. There's simply less oxygen available for combustion. Without intervention, an engine at that altitude would gasp and wheeze, producing only a fraction of its rated horsepower. The turbocharger solved this problem through an ingenious use of waste energy. The hot exhaust gases leaving the engine, gases that would otherwise simply dissipate into the atmosphere, were channeled through a turbine wheel. This wheel, spinning at tremendous speeds, up to 21,000 revolutions per minute, drove a compressor on the opposite end of the shaft. The compressor sucked in the thin, high-altitude air and squeezed it, compressed it, forced those oxygen molecules closer together. This compressed air then flowed through an intercooler to reduce its temperature before entering the engine cylinders. The result was an engine that could maintain sea-level power output even in the thin air 5 miles above the Earth. For the B-17, this technology was the difference between life and ending. A bomber that could reach 25 to 30,000 feet could fly above much of the German anti-aircraft artillery. The dreaded 88mm flak guns, while still dangerous, lost accuracy and effectiveness at extreme altitude. More crucially, German fighters, most of which lacked effective supercharging, struggled to reach the heights where the fortresses flew in formation. The Luftwaffe's Messerschmitt Bf-101Is and Focke-Wulf 190s could chase the bombers upward, but at 28 or 30,000 feet, the German fighters were operating at the edge of their performance envelope, sluggish and vulnerable. Every 1,000 feet of additional altitude a B-17 could achieve meant better odds of survival. It meant the difference between coming home with all 10 crew members intact or becoming another statistic in the mounting toll of the strategic bombing campaign. It meant widows and orphans or fathers returning to their children. It meant everything. Jimmy Donovan understood this in his bones. He had been a crew chief since the 303rd Bomb Group arrived in England in late 1942. He had watched crews take off in the gray dawn and counted the planes returning in the afternoon, noting with a sinking heart when one or two or sometimes more failed to appear. He had seen the bullet holes, the flak damage, the hydraulic fluid and blood mixing on the aluminum floor panels. He had held young pilots as they wept over lost friends. The war had aged him beyond his 24 years. But Jimmy had a gift. Before the war, he had worked in his father's garage in Michigan, rebuilding engines for farmers and truckers. He had developed an intuitive sense for mechanical systems, an ability to diagnose problems that others missed. When he enlisted in the Army Air Forces, this talent was recognized, and he was assigned to the technical school at Chanute Field, where he learned everything the military could teach about the B-17 Flying Fortress. He had graduated at the top of his class. Now, standing under Lucky Strike in the freezing darkness, Jimmy was thinking about a problem that had been nagging at him for weeks. The B-17s were experiencing inconsistent performance at high altitude. Some days, some aircraft, they climbed like angels, reaching 30,000 feet with relative ease. Other days, other aircraft, they struggled, maxing out at 26 or 27,000 feet, wallowing in the thin air while German fighters prowled above them like sharks. The pilots attributed it to differences between individual aircraft. The engineering officers blamed variations in bomb loads or fuel quantities. The squadron commander suspected sabotage, though no evidence was ever found. But Jimmy suspected something else, something he had been noticing in the pattern of which aircraft performed well and which struggled. The turbochargers were sensitive devices, far more complex than the engines they served. Each one contained hundreds of precisely machined parts operating under extreme conditions of temperature, pressure, and rotational speed. The turbine wheel, exposed to exhaust gas temperatures exceeding 1,300 degrees Fahrenheit, had to be made from special steel alloys. The bearings supporting the spinning shaft had to function with almost no tolerance for error. Even a small imbalance, a slight misalignment, could cause the turbocharger to lose efficiency or, worse, to fail catastrophically. The technical orders from Wright Aeronautical and General Electric specified the maintenance procedures: check the turbine blades for damage, ensure proper oil flow to the bearings, verify the wastegate operation, inspect the intercooler for leaks. Jimmy performed all these checks religiously. But he had noticed something the technical orders didn't mention, something subtle that only someone who truly understood these machines might observe. The turbochargers were mounted beneath the nacelles, exposed to the slipstream, bolted directly to the engine's exhaust system. During operation, the entire assembly absorbed heat from the exhaust gases. When the aircraft landed and the engines shut down, the turbochargers began to cool. Metal, as it cools, contracts. Different metals contract at different rates. The turbine housing, made from high-temperature steel, contracted at a different rate than the aluminum ducting connecting it to the intercooler. The steel mounting bolts contracted at yet another rate. Over time, over dozens of missions, this constant cycle of heating and cooling caused the mounting bolts to work slightly loose. Not loose enough to be visible during inspection, not loose enough to cause an obvious malfunction, but loose enough to allow tiny amounts of compressed air to leak from the joints between the turbocharger and the ducting. Lose just 5 or 10% of the compressed air to leakage, and the engine lost power at altitude. The difference might be only a few thousand feet of ceiling, but in combat, those few thousand feet could mean survival. The technical orders specified torque values for the mounting bolts, checked during major overhauls. But the overhaul schedule was based on flight hours, and it didn't account for the number of heating and cooling cycles or the stress of combat operations. Aircraft that flew missions frequently, experiencing more heating cycles, developed looseness faster than aircraft used less intensively, but the pattern wasn't obvious unless someone was looking for it specifically. Jimmy had started paying attention several weeks earlier after a particularly bad mission. Lucky Strike and her sister ship, Memphis Belle Jr., had flown together to bomb the ball-bearing factories at Schweinfurt. Both aircraft were B-17Gs from the same production block, built within days of each other at Boeing's Seattle plant. They carried identical bomb loads, had nearly identical fuel quantities, and were crewed by pilots of comparable skill. Yet Memphis Bell Jr. had struggled to reach altitude, topping out at 26,000 feet, while Lucky Strike climbed easily to 29,000. The difference had put Memphis Bell Jr. directly in the killing zone of the German 88mm guns. A single shell had torn through her No. 3 engine, forcing the crew to shut it down and drop out of formation. Flying alone, without the mutual protection of the combat box, Memphis Bell Jr. became a target for Luftwaffe fighters. She had made it home, but barely, with 3 crew members wounded and 2 engines shot out. Jimmy had been haunted by the sight of that damaged aircraft limping back to base. Could he have prevented it? Could better maintenance have given Memphis Bell Jr. those extra 3,000 feet of altitude? The question drove him to investigate. He began conducting his own unofficial tests, checking the mounting bolt torque on every aircraft in the squadron during his routine inspections. He didn't tell anyone what he was doing. The engineering officers might have seen it as questioning their procedures, and Jimmy had no desire to cause conflict. He simply wanted to understand the pattern. What he found confirmed his suspicions. Aircraft that had flown more missions showed more looseness in the turbocharger mountings. The correlation wasn't perfect. There were other factors at play: engine wear, variations in intercooler efficiency, differences in the turbine wheels themselves, but the pattern was clear enough. Jimmy started a maintenance log recording the mounting bolt torque for every aircraft, along with the pilot's reports of high-altitude performance. The correlation strengthened. Now, in the pre-dawn darkness of February 12, 1944, Jimmy was putting his theory to the test. Lucky Strike was scheduled for a maximum effort mission, one of the deep penetration raids that the 8th Air Force had resumed after the arrival of long-range fighter escorts. The target was a Messerschmitt factory near Regensburg, deep in southern Germany. It would require every foot of altitude Lucky Strike could achieve. Jimmy had spent the previous evening carefully checking and retorquing every mounting bolt on all 4 of Lucky Strike's turbochargers. He had used his personal torquey wrench, calibrated more precisely than the squadron's standard equipment. He had worked slowly, methodically, feeling the resistance as each bolt reached the specified torque, then adding just a fraction more. The exact amount that his experience told him would compensate for the thermal cycling. But he had done something else too, something that went beyond the technical orders, something that he had been developing over weeks of observation and experimentation. He had adjusted the wastegates. The wastegate was a critical component of the turbocharger system. As the turbocharger compressed air, it built up pressure, measured as manifold pressure in inches of mercury. Too much pressure could damage the engine. The wastegate was essentially a valve that bypassed exhaust gas around the turbine wheel, reducing its speed and thus limiting the maximum boost pressure. An automatic regulator controlled the wastegate, opening it as necessary to prevent overboost conditions. But the regulators, like everything else on these aircraft, were set to conservative values. The engineers who designed them had built-in safety margins to protect the engines under all possible conditions. This was sound engineering practice for peacetime operations, but this wasn't peacetime. This was war, and sometimes survival meant pushing the equipment beyond its conservative design limits. Jimmy had noticed that the wastegates on some aircraft opened earlier than necessary, limiting boost pressure before the engines reached their maximum safe manifold pressure. He suspected that the automatic regulators, like the mounting bolts, were affected by the thermal cycling of combat operations. The springs and diaphragms in the regulators gradually lost calibration, causing them to activate prematurely. The solution was delicate. Jimmy couldn't simply prevent the wastegates from opening. That would risk catastrophic engine damage from overboost. but he could adjust the activation point, resetting the regulators to their original factory calibration. The technical orders didn't specifically call for this adjustment during routine maintenance. It was supposed to be done only during major overhauls. But Jimmy had taught himself to do it carefully, precisely, checking and rechecking his work. The risk was real. If he made an error, if he set the wastegate to activate too late, the resulting overboost could cause cylinder head cracking, bearing failure, or even catastrophic engine destruction. A failed engine over Germany meant the aircraft would have to drop out of formation, becoming vulnerable to fighter attack. Worse, if multiple engines were damaged, the aircraft might not make it home at all. But Jimmy had confidence in his work. He had tested his adjustments on several aircraft during practice flights, having enlisted sympathetic pilots to monitor the manifold pressures and report altitude performance. The results had been consistent. Aircraft with properly torqued mounting bolts and correctly calibrated wastegates gained an additional 2,000 to 3,000 feet of service ceiling. It wasn't a dramatic improvement, but in the narrow margins of aerial combat, it could mean the difference between survival and destruction. As the first gray light of dawn began to illuminate the airfield, the crew of Lucky Strike arrived. Lieutenant Robert Morrison, the pilot, was a lanky Texan with an easygoing manner that concealed a fierce determination. His co-pilot, Lieutenant Thomas Chen, was a first-generation Chinese-American from San Francisco, flying combat missions while his parents were held in an internment camp back home, a bitter irony none of them discussed. The bombardier, Lieutenant Paul Kovacs, was a former mathematics teacher from Cleveland. The navigator, Lieutenant William Bill Hayes, had studied astronomy at Yale before the war. The 6 enlisted men, the flight engineer, radio operator, and 4 gunners were a cross-section of America, farm boys and city kids, mechanics and factory workers, united by a common purpose. Jimmy met them at the hardstand going through the pre-flight briefing with Lieutenant Morrison. The pilot trusted Jimmy completely. They had flown together since the squadron's early days in England, and Morrison knew that Lucky Strike was always in top condition under Jimmy's care. As they talked, Jimmy made a decision. He would tell Morrison about the adjustments he had made. Not the technical details. Pilots didn't need to know about torque values and wastegate calibrations. But he wanted Morrison to know that Lucky Strike should perform better at altitude today. He wanted the pilot to push for every foot of ceiling the aircraft could achieve. "Sir," Jimmy said, his voice low enough that the other crew members couldn't hear, "I've made some adjustments to the turbochargers, nothing outside the technical specs, but I think she'll climb better today. When you're forming up, don't be surprised if you find yourself higher than usual for the same power setting." Morrison looked at him thoughtfully. The pilot knew Jimmy never made casual statements about aircraft performance. If the crew chief said the plane would climb better, there was a reason. "How much better?" Morrison asked. "Maybe 2,000 to 3,000 feet additional ceiling, maybe more if conditions are right." Morrison whistled softly. "That would put us at 31,000 to 32,000 feet. That's higher than most of the group has ever flown in combat." "Yes, sir, but it might keep you above the worst of the flak, and the German fighters can't follow you that high, not effectively." Morrison nodded slowly. "Okay, Jimmy, I trust your work. We'll see how high she'll take us." The crew climbed aboard, and Jimmy supervised as his ground crew performed the final checks. The 4 Wright Cyclones coughed to life one by one, their propellers cutting through the cold air with a sound that always sent a thrill through Jimmy's chest. There was something primal about the sound of radial engines at full power, a mechanical thunder that spoke of barely controlled violence. Lucky Strike taxied out to the runway, joining the long line of B-17s preparing for takeoff. 36 aircraft from the 303rd Bomb Group would fly today, joining hundreds more from other groups for a massive raid deep into Germany. The assembly of such a large formation was a complex ballet, each group climbing to its assigned altitude, joining with other groups to form wings, the wings combining into air divisions. The entire process took over an hour and consumed enormous quantities of fuel. Jimmy watched from the ground as Lucky Strike accelerated down the runway, her tail coming up, then her main landing gear leaving the concrete. She climbed steadily into the gray English sky, disappearing into the clouds within minutes. He wouldn't see her again for 8 hours, maybe more. All he could do was wait and hope that his work had been good enough. The mission to Regensburg was a maximum effort, involving over 800 bombers protected by nearly 500 fighter escorts. The Luftwaffe rose to meet them in force, throwing hundreds of fighters into the battle. The sky over Germany became a chaotic melee of aircraft, contrails, tracer fire, and falling bombs. For the crew of Lucky Strike, the first indication that something was different came during the climb to formation altitude. Lieutenant Morrison had set the climb power according to standard procedures, but he noticed the altimeter winding up faster than usual. By the time Lucky Strike reached the group's assembly point, she was 500 feet higher than expected. Morrison had to reduce power slightly to avoid overshooting the formation altitude. During the long flight across the English Channel and over occupied France, Lucky Strike maintained position easily. The bomber felt responsive, powerful, and as they approached the German border and began climbing to combat altitude, Morrison decided to test Jimmy's promise. Instead of leveling off at the group's assigned altitude of 28,000 feet, he kept climbing, watching the formation drop slightly beneath him. At 29,000 feet, the other bombers of the 303rd leveled off, settling into the combat box formation that provided mutual defensive fire. Morrison continued climbing, 30,000 feet, 31,000. At 32,000 feet, Lucky Strike finally seemed to reach her limit, the rate of climb dropping to less than 100 feet per minute. Morrison leveled off, and only then did he realize what Jimmy's adjustments had given him. Lucky Strike was flying 4,000 feet higher than the rest of the formation. They were alone. For a moment, Morrison felt a spike of fear. The strength of the B-17 defensive formation lay in mutual support, dozens of aircraft flying close together, their combined firepower creating an almost impenetrable box of defensive fire. A bomber flying alone was vulnerable, an easy target for German fighters. But then Morrison looked down at the formation below and understood. The German fighters were concentrating on the main formation, attacking from all angles, their pilots knowing they had to press through the defensive fire to reach the bombers. Very few fighters were climbing to Lucky Strike's altitude. At 32,000 feet, the Messerschmitts and Focke-Wulfs were operating at the ragged edge of their performance. They were slow, their controls sluggish in the thin air. The few that did attempt to attack Lucky Strike found themselves unable to maintain the speed needed for effective gunnery. Moreover, the flak, those deadly bursts of anti-aircraft fire that turned the sky into a hellscape of black clouds and shrapnel, was concentrated at the altitude of the main formation. At 32,000 feet, Lucky Strike was above the optimal burst height of most German anti-aircraft artillery. The flak still reached them, but it was less accurate, the shells detonating below and to the side of the aircraft. Morrison made a decision. Instead of trying to rejoin the formation, he would complete the bomb run from his current altitude. He called Lieutenant Kovacs, the bombardier, on the intercom. "Paul, we're going to be bombing from 4,000 feet above the group. Can you make the necessary adjustments on the Norden?" There was a pause as Kovacs calculated. The Norden bomb site was a marvel of mechanical computation, but it required accurate inputs of altitude, airspeed, and wind conditions. Bombing from an unexpected altitude would require recalculation. "I can do it, sir," Kovacs responded. "Give me 2 minutes to input the new data." As Lucky Strike approached the initial point, the landmark where bombers began their final straight-line approach to the target, Morrison could see the entire battle laid out below him. The main formation, flying at 28,000 feet, was taking heavy punishment from both fighters and flak. Aircraft were trailing smoke, some with engines on fire. Here and there he could see the white blossoms of parachutes as crews bailed out of stricken bombers. The sky was laced with contrails, each one marking the path of an aircraft, creating a maze of white lines against the blue. From his vantage point, 4,000 feet above, Morrison could see things the other pilots couldn't. He could see where the flak batteries were concentrated, could see the approach paths of German fighter formations before they reached the bomber stream. It was like being a spectator at a horrific sporting event, watching from the stands as the players fought for their lives on the field below. The bomb run seemed to take forever. Once the bombardier activated the Norden bomb sight and coupled it to the aircraft's autopilot, Morrison's job was to sit still and maintain altitude and airspeed. For those endless minutes, Lucky Strike flew straight and level, a perfect target for any fighter or flak gun that could reach her altitude. Morrison's hands gripped the control wheel, his knuckles white, resisting every instinct that screamed at him to take evasive action. "Bombs away!" Kovach's voice crackled through the intercom, and Morrison felt the aircraft lurch upward as 4,000 pounds of high-explosive bombs dropped free. He immediately banked the bomber into a turn, breaking away from the target, no longer constrained by the need to maintain course for the bomb site. As Lucky Strike turned for home, Morrison took stock of the situation. All 4 engines were running smoothly. No major damage from fighters or flak. All crew members reporting in as okay. They had dropped their bombs on target. The bombardier reported seeing the explosions near the aiming point. And they still had enough altitude to stay above most of the defenses on the long flight home. The return journey was tense but less eventful than the inbound leg. German fighters, low on fuel and ammunition, broke off their attacks. The flak, while still present, was scattered and inaccurate. Lucky Strike maintained her altitude advantage, and as they crossed back over the English Channel, Morrison finally allowed himself to believe they would make it home. The landing at Molesworth was routine, and as Morrison taxied Lucky Strike back to her hardstand, he could see Jimmy waiting. The crew chief stood beside a fire truck, his eyes locked on the approaching bomber, checking for damage, counting the crew members as they emerged from the hatches. Morrison shut down the engines and climbed out, his legs unsteady after 8 hours in the cockpit. He walked over to Jimmy, pulling off his oxygen mask and flight helmet. "Jimmy," he said, his voice hoarse, from breathing pure oxygen for hours, "I don't know what you did to this aircraft, but it saved our lives today. We climbed to 32,000 feet and stayed there the entire mission. The fighters couldn't reach us. The flak couldn't reach us. We were above everything." Jimmy felt a wave of relief wash over him. His adjustments had worked. His theory had been correct, but more importantly, his crew had come home safe. Over the following weeks, Morrison reported Lucky Strike's performance to the engineering officers. At first, there was skepticism. Some of the officers suspected Morrison of exaggerating or perhaps misreading his instruments. But when other crews began reporting improved high-altitude performance from aircraft that Jimmy had serviced, the pattern became impossible to ignore. Jimmy was called in to explain his procedures. He brought his maintenance logs, his torque readings, his notes on wastegate calibration. The engineering officers listened, initially skeptical, then increasingly interested. What Jimmy had discovered through practical experience was something the engineering manuals had missed. The technical orders assumed that properly maintained turbochargers would remain properly maintained. They didn't account for the gradual degradation caused by combat operations, the loosening of mounting bolts, the drift in wastegate calibration. Jimmy's solution was elegant in its simplicity, more frequent checking of mounting bolt torque, particularly on aircraft flying intensive combat schedules. Periodic recalibration of the wastegate regulators, not just during major overhauls, but after every 50 hours of flight time. These weren't radical departures from standard procedures, they were refinements, adjustments based on operational experience, rather than laboratory testing. The 3rd Bomb Group began implementing Jimmy's procedures across all their aircraft. Within a month, the entire group was consistently achieving higher combat altitudes. Other bomb groups heard about the improvements and requested information. The 8th Air Force Headquarters took notice and began distributing technical bulletins based on Jimmy's discoveries. But here's where the story takes a strange turn, where a significant contribution to the war effort began its journey into obscurity. The technical bulletins that were distributed didn't mention Jimmy Donovan by name. They were written by engineering officers who translated Jimmy's practical, hands-on knowledge into official technical language. The bulletin spoke of improved maintenance procedures for turbo-supercharger mounting systems and enhanced wastegate calibration protocols. They were dry bureaucratic documents that gave no hint of the individual insight and dedication that had led to the discoveries. Moreover, as the war progressed, aircraft technology evolved rapidly. The B-17s, while still effective, were gradually supplemented and then replaced by newer bombers, the B-29 Superfortress with its more advanced pressurization and engine systems. The specific techniques that Jimmy had developed for maintaining B-17 turbochargers became less relevant as the war moved into its final phase. After the war, when historians began writing about the strategic bombing campaign, their focus was on the big picture. They wrote about the generals who planned the raids, the pilots who flew the missions, the strategic decisions that shaped the air war over Europe. The ground crews, the mechanics, the crew chiefs who kept the aircraft flying, they were mentioned in passing, if at all. They were seen as support personnel, important certainly, but not central to the narrative of aerial combat. Jimmy Donovan himself contributed to this obscurity. Like many veterans of his generation, he didn't talk much about his war experiences after returning home to Michigan. He went back to working in his father's garage, eventually taking it over and running it successfully for decades. He married, raised a family, lived a quiet, productive life. When people asked about his time in the service, he would say simply that he had been a crew chief on B-17s in England, maintaining the aircraft that flew missions over Germany. He rarely elaborated, and he never mentioned his contributions to improving high-altitude performance. The few times that military historians or aviation enthusiasts sought him out, usually in connection with reunions of the 303rd Bomb Group or interviews about B-17 operations, Jimmy deflected credit. He would insist that he had simply done his job, that any competent crew chief would have noticed the same things he had noticed. He spoke with far more enthusiasm about the pilots and air crews he had served, telling stories of their courage and sacrifice, making sure their names were remembered. But the truth is that Jimmy Donovan made a significant contribution to the Allied victory in the air war over Europe. His insights into turbocharger maintenance allowed B-17s to fly higher, increasing their survivability against both flak and fighters. How many lives were saved because bombers could climb those additional 2,000 or 3,000 feet? How many aircraft made it home because they could stay above the worst of the defenses? We'll never know the exact numbers, but the impact was real and measurable. The irony is that Jimmy's discoveries weren't revolutionary in the sense of being new technology. The principles of turbocharger operation were well understood by the engineers who designed them. The maintenance procedures he developed were refinements of existing techniques, not radical departures. What Jimmy brought to the problem was something that couldn't be taught in technical schools or written in manuals. He brought practical experience, careful observation, and a deep understanding of how machines behave under real-world conditions. This is a pattern we see repeatedly in military history: the gap between laboratory performance and field performance, between how equipment is supposed to work according to the specifications and how it actually works in combat conditions. Bridging that gap requires people like Jimmy Donovan, people who understand both the theory and the practice, who can translate between the language of engineers and the reality of the flight line. As we think about the strategic bombing campaign over Europe, We usually picture the formations of silver bombers crossing the sky, the fighter escorts wheeling overhead, the black puffs of flak bursting among them. We imagine the bomb runs over German cities and factories, the devastating impact of high explosives raining down from above. This is the dramatic, visible face of the air war. But behind every one of those missions, behind every bomber that took off and hopefully returned safely, there were ground crews working through the night. There were mechanics troubleshooting engine problems, armorers loading bombs and ammunition, fuel truck crews topping off tanks. And there were crew chiefs like Jimmy Donovan who understood that keeping these complex machines flying wasn't just about following procedures in a manual. It was about understanding the machines, listening to them, feeling their rhythms, and knowing when something wasn't quite right, even if all the gauges read normal. The B-17 Flying Fortress has been called one of the most important aircraft of World War II, and rightly so. Nearly 13,000 of them were built, and they dropped roughly half of all the bombs that fell on Germany during the war. They became symbols of American air power, their distinctive shape and sound recognized by people on both sides of the conflict. Books, movies, and documentaries have told their story from every conceivable angle. Yet, for all the attention paid to the B-17, certain aspects of its story remain obscure. We know about the famous aircraft, the ones with colorful nose art and dramatic histories. Memphis Belle completed 25 missions and became the subject of a documentary and later a feature film. Yankee Doodle Dandy, which led the first American daylight raid on occupied Europe, Hell's Angels, which survived 48 missions despite heavy damage. These aircraft are remembered, celebrated, preserved in museums. But what about the thousands of B-17s that flew mission after mission without achieving particular fame? What about the hundreds of crew chiefs who kept them flying, who worked through brutal English winters and scorching summer days, who scrounged parts and improvised repairs and somehow kept aging, battle-damaged aircraft operational? Their stories are largely forgotten, relegated to footnotes in the official histories, if mentioned at all. Jimmy Donovan's technique for maintaining optimal turbocharger performance represents a perfect example of this forgotten knowledge. The improvements he documented were real and significant. They were implemented across multiple bomb groups and contributed to the success of the strategic bombing campaign. Yet within a few years of the war's end, the specifics of his procedures had faded from institutional memory. The technical bulletins were filed away and forgotten as the B-17 itself was retired from service. When I began researching this story, I was struck by how difficult it was to find information about ground crew contributions to aircraft performance. The official histories of the 8th Air Force focus on command decisions, mission statistics, and aircrew experiences. Technical manuals document procedures, but rarely explain the reasoning behind them. Personal memoirs by pilots and gunners mention their crew chiefs only in passing, and then usually just to praise their dedication without explaining the details of their work. It took months of digging through archives, tracking down veterans willing to be interviewed, and piecing together fragments of information from multiple sources to reconstruct what Jimmy Donovan had accomplished. Even then, I cannot claim to know the full story. Much of it has been lost to time, taken to graves by men who never thought their contributions were worth recording for history. What we do know is this. In February of 1944, at a bomber base in England, a crew chief noticed a pattern that others had missed. He developed a solution based on practical experience and careful observation. He tested his theory and proved it worked. He shared his knowledge, and that knowledge spread, contributing to improved performance and ultimately to saving lives. Then, as often happens in war, the urgency of the present moment pushed aside the memory of how the problem had been solved. The technique became routine, the innovation became standard procedure, and the innovator returned to civilian life carrying his knowledge but not his fame. There is a broader lesson here about how we remember wars and the people who fought them. We naturally gravitate toward stories of individual heroism, dramatic moments, decisive battles. We remember the generals and the fighter aces, the bombers that completed impossible missions, the attacks that turned the tide of war. These stories are important, certainly. They capture the drama and sacrifice that defined the conflict. But wars aren't won solely by dramatic moments and individual heroism. They're won by logistics, by maintenance, by the accumulated effect of thousands of small improvements and refinements. They're won by people like Jimmy Donovan, who never flew a combat mission, but whose work allowed others to fly theirs with better odds of survival. They're won by the unglamorous work of keeping machines running, keeping supplies flowing, keeping the vast military machine operational, day after day, month after month, year after year. As we approach the 80th anniversary of the end of World War II, very few of the people who participated in that conflict are still alive. The pilots, gunners, mechanics, and ground crew are passing into history, taking their memories and experiences with them. When we lose the last of these veterans, we lose something irreplaceable. Not just their first-hand accounts of events, though those are valuable. We lose their experiential knowledge, the kind of understanding that comes only from having been there, from having done the work, from having lived through the urgency and chaos and improvisation that characterized the war years. Jimmy Donovan passed away in 1998 at the age of 78. His obituary in the local Michigan newspaper mentioned his military service briefly. It noted that he had been a staff sergeant in the Army Air Forces, that he had served in England during the war, and that he had received a commendation for outstanding service. It mentioned his family, his work as a mechanic, his involvement in the local community. It was a typical obituary for a typical veteran, giving no hint of his specific contributions to the war effort. I discovered Jimmy's story almost by accident. I was researching a different aspect of B-17 operations when I came across a reference in a technical bulletin from 1944, something about improved turbocharger maintenance procedures developed by ground personnel in the 303rd Bomb Group. The bulletin didn't name names, but it provided enough detail that I could start asking questions of veterans organizations and historical societies. One lead led to another, and eventually I found a nephew of Jimmy's who had some of his uncle's papers, including the maintenance logs that Jimmy had kept documenting his observations and procedures. Those logs are remarkable documents. They're written in pencil, the pages yellowed and brittle with age. Jimmy's handwriting was small and precise, the notations abbreviated in ways that probably made sense to him, but required considerable effort to decipher decades later. But once I understood what I was reading, I realized I had found something significant. These were the field notes of someone conducting his own unauthorized research project, testing a hypothesis, documenting results, refining his techniques based on empirical observation. This was science conducted not in a laboratory, but on a bomber base in wartime England. This was the scientific method applied by someone who probably never used that term to describe what he was doing. He saw a problem, formed a hypothesis about its cause, tested that hypothesis, and refined his solution based on the results. Then he shared his findings so others could benefit from them. In any other context, this would be recognized as a legitimate contribution to engineering knowledge. But because it happened in a military setting, because Jimmy was an enlisted man rather than an officer or civilian engineer, because the specific technology involved was soon obsolete, the contribution was forgotten. I want to be clear that I'm not trying to elevate Jimmy Donovan to the status of a war hero in the traditional sense. He would have been the first to reject such designation. He didn't storm any beaches or shoot down any enemy aircraft. He didn't lead any charges or make any last stands. What he did was work quietly and competently to make the aircraft in his care perform as well as they possibly could. He noticed things that needed improvement and figured out how to improve them. He shared his knowledge freely, without thought of personal recognition or reward. In a way, that's what makes his story so powerful. Jimmy Donovan represents thousands, perhaps tens of thousands, of similar stories from World War II and every other war. Stories of people who did their jobs exceptionally well, who made small but significant improvements to equipment or procedures, who contributed to victory in ways that never made headlines. Most of these stories will never be told because the people involved didn't think they were doing anything remarkable, and because historians focus on the bigger picture. But the bigger picture is made up of all these small stories, all these individual contributions. The strategic bombing campaign succeeded not just because the Allied air forces had superior numbers and eventually air superiority. It succeeded because of the accumulated effect of countless refinements and improvements. Better training for pilots and gunners, better formation tactics, better navigation techniques, better fighter escort procedures, better maintenance practices. Each improvement considered in isolation might seem minor, but taken together, they made the difference between a marginally effective bombing campaign and one that played a crucial role in defeating Nazi Germany. Jimmy Donovan's technique for optimizing B-17 turbocharger performance was one small piece of that larger puzzle. The additional 2,000 or 3,000 feet of altitude that his procedures provided didn't guarantee safety. Aircraft maintained according to his techniques still fell to fighters and flak, but they fell less often. The survival rates improved, even if only by a few percentage points. And over the course of hundreds of missions involving thousands of aircraft, those few percentage points translated into lives saved and missions completed. I think about the crews who flew in aircraft that Jimmy had serviced. Did they know about the adjustments he had made? Did they understand why their bombers seemed to climb more easily than others? Why they could reach altitudes that put them above the worst of the danger? Probably not. To them, the aircraft either performed well or didn't, and they had little insight into the reasons behind the variations. They trusted their ground crews to keep the aircraft in good condition, but they didn't necessarily understand the details of that maintenance. Lieutenant Robert Morrison and the crew of Lucky Strike were an exception. Morrison knew about Jimmy's work because Jimmy had told him directly. After that first mission to Regensburg, Morrison made a point of seeking out Jimmy after every flight, debriefing not just with the engineering officers, but with his crew chief. They developed a partnership, sharing information about how the aircraft performed in combat conditions and discussing possible modifications or adjustments. This relationship was unusual, but not unique. Throughout the 8th Air Force, there were similar partnerships between conscientious crew chiefs and attentive pilots. These relationships weren't officially documented or even officially recognized. They simply developed naturally when people who cared about their work and their comrades collaborated to improve outcomes. The military hierarchy didn't necessarily encourage such collaboration. Enlisted men weren't expected to provide technical feedback to officers, but neither did it actively discourage it, as long as the chain of command was respected. Lucky Strike and her crew completed 35 combat missions during 1944, surviving the intense air battles over Germany and occupied Europe. Several times, Morrison credited their high-altitude capability with saving the aircraft from destruction. There were missions where other bombers in the formation were shot down, while Lucky Strike, flying 1,000 feet higher, escaped relatively unscathed. Morrison knew that this advantage came from Jimmy's maintenance work, and he made sure to mention it in his reports and in conversations with other pilots. But even this acknowledgement wasn't enough to preserve Jimmy's contribution in the historical record. Morrison himself was shot down on a subsequent mission flying a different aircraft and spent the last months of the war as a prisoner. By the time he returned home, the war was over. The urgency of combat operations had faded, and the details of maintenance procedures seemed less important than they had in the heat of battle. Like most veterans, Morrison focused on rebuilding his civilian life rather than on preserving wartime memories. This pattern of forgetting extends beyond individual stories to encompass entire categories of wartime experience. Ground crews, maintenance personnel, supply officers, administrative staff, all the people who made combat operations possible but didn't directly participate in combat, their contributions have largely disappeared from popular understanding of the war. When we think about World War II in the air, we think about the pilots and gunners, not the mechanics. We think about the bombing missions, not the hours of maintenance work required to launch those missions. Part of this stems from the natural human tendency to focus on the dramatic and visible. Air combat is inherently dramatic. Planes wheeling through the sky, guns firing, aircraft exploding or trailing smoke as they fall. Maintenance work is inherently undramatic. People with wrenches and gauges, checking specifications, adjusting settings, replacing worn parts. It's hard to build a compelling narrative around routine maintenance, even when that maintenance is crucial to success. But part of it also stems from the structure of military recognition and remembrance. The military award system recognizes acts of valor in combat. It's designed to honor those who face enemy fire, who risk their lives in dramatic moments of danger. There are no medals for noticing that mounting bolts work loose over time, or for figuring out how to recalibrate wastegates. The contributions of people like Jimmy Donovan fall outside the framework of how the military traditionally recognizes excellence. This isn't to say that ground crews went completely unrecognized during the war. Many crew chiefs received commendations for outstanding service. Some were promoted to higher ranks. The importance of maintenance was acknowledged in official communications and training materials. But acknowledgement during wartime is different from remembrance in peacetime. Once the shooting stopped, once the urgency faded, the specific details of who did what and why began to blur together. Today, when we visit air museums and see preserved B-17s, we're seeing aircraft that have been restored to pristine condition. The engines have been rebuilt, the systems overhauled, the aluminum skin polished to a mirror shine. They look as they might have looked rolling off the assembly line in 1944, before they ever saw combat, before they ever experienced the wear and tear of combat operations. They're beautiful, impressive machines, and they help us understand what these bombers looked like and how they were constructed. But what we don't see, what cannot be preserved in a museum, is the operational reality of keeping these aircraft flying under wartime conditions. We don't see the crew chiefs working through the night in freezing temperatures, troubleshooting engine problems by flashlight. We don't see the improvised repairs made with salvaged parts because proper replacements weren't available. We don't see the careful adjustments and refinements that mechanics like Jimmy Donovan developed through experience and observation. All of that, the accumulated practical knowledge of thousands of ground crew members, has largely been lost to time. Some of it was recorded in technical manuals and maintenance bulletins, preserved in archives if anyone cares to look for it. But much of it existed only in the minds and hands of the mechanics themselves, experiential knowledge that couldn't be fully captured in written form. How do you write down the feel of a bolt that's been torqued correctly versus one that's just slightly loose? How do you describe the sound of an engine that's running well versus one that has a problem that hasn't yet shown up on the gauges? This was the kind of knowledge that Jimmy Donovan possessed, and it's exactly the kind of knowledge that's hardest to preserve and transmit. As I've studied this story and tried to understand its significance, I've come to see it as emblematic of a larger truth about war and technology. We tend to think of technological advantage in terms of new inventions, superior designs, breakthrough innovations, and certainly those things matter. The B-17's turbochargers represented a technological advantage over aircraft without such systems. The Norden bomb sight was a sophisticated piece of technology that gave American bombers an edge in accuracy. These innovations mattered. But technological advantage isn't just about having the best equipment. It's also about using that equipment effectively, maintaining it properly, getting the most out of it under real-world conditions. The Germans had technically sophisticated aircraft and weapons, some of them more advanced than their Allied counterparts. But as the war progressed, German industry couldn't keep up with Allied production. German maintenance suffered from shortages of parts and trained personnel, and German operational procedures failed to maximize the capabilities of their equipment. The Allies won the air war over Europe not just because they had good aircraft, but because they had the industrial capacity to produce them in enormous numbers, the training infrastructure to prepare crews to fly them, the logistics system to supply them, and the maintenance organization to keep them operational. At every level, from design to production to operation to maintenance, the Allied system worked better than the German system, and people like Jimmy Donovan were part of that system, contributing in their own way to its overall effectiveness. I want to emphasize again that there was nothing unique or irreplaceable about Jimmy Donovan specifically. He would have been the first to insist on this point. The techniques he developed for maintaining turbochargers could have been discovered by many other competent crew chiefs. The observations he made about mounting bolt torque and wastegate calibration weren't particularly profound or complicated. Any mechanic with sufficient experience and attention to detail might have noticed the same things. What makes Jimmy's story significant isn't that he was uniquely talented or that his discoveries were revolutionary. What makes it significant is that it illustrates a process. It shows how practical knowledge develops in response to real-world problems. It shows how improvements happen incrementally through observation and refinement, rather than sudden breakthroughs. And it shows how these incremental improvements, multiplied across thousands of aircraft and millions of flight hours, contribute to success in ways that are difficult to quantify but nonetheless real. When historians write about the strategic bombing campaign, they focus on the big numbers: how many aircraft took off, how many reached their targets, how many bombs were dropped. What percentage of German industrial capacity was destroyed? These are important metrics, and they tell part of the story, but they don't capture the human dimension, the countless individual decisions and actions that made those missions possible. Every one of those bombers that took off represented hundreds of hours of maintenance work. Every successful mission represented correct decisions made by dozens of people, pilots navigating accurately, bombardiers aiming precisely, gunners defending effectively. And behind all of it was the infrastructure of support, the people who never flew combat missions, but whose work made combat missions possible. Jimmy Donovan's forgotten trick, his technique for optimizing turbocharger performance, represents all of these forgotten contributions. It's a reminder that victory in war isn't just about the heroes and the dramatic moments. It's about the accumulated effect of thousands of people doing their jobs well, finding small ways to improve outcomes, sharing their knowledge with others. It's about the mechanics and the logistics specialists and the administrative clerks and all the other people whose work was essential but rarely acknowledged. As the generation that fought World War II passes into history, we have an obligation to remember their stories, all their stories, not just the ones that fit easily into heroic narratives. We need to remember the ground crews who kept the aircraft flying. We need to remember the people who solved unglamorous but important problems. We need to remember that war is a collective effort requiring contributions from people in all roles, and that victory comes from the sum of all those contributions. Jimmy Donovan's story might have been lost completely if not for chance and persistence in research. How many other similar stories have been lost? How many other crew chiefs and mechanics and specialists made their own discoveries and improvements that contributed to the war effort but were never recorded or remembered? We'll never know the full count, and that's a loss not just for historical knowledge, but for our understanding of how complex systems function and how improvements happen. I hope that by telling Jimmy's story, by pulling it out of obscurity and presenting it to a wider audience, I can honor not just him specifically, but all the people like him. The ground crews and support personnel who made victory possible, but whose names don't appear in the history books. The mechanics who understood machines in ways that went beyond what the manuals taught. The people who saw problems and fixed them, who made things work better, who shared their knowledge freely without thought of recognition or reward. In the end, that's what Jimmy Donovan's forgotten trick represents. Not just a technical improvement to B-17 turbochargers, though it was that. Not just a contribution to the strategic bombing campaign, though it was that too. It represents a larger truth about how we win wars and how we lose them, about what gets remembered and what gets forgotten, about the importance of honoring all forms of service and contribution, not just the ones that fit our preconceptions of heroism. The B-17 flying fortresses that crossed the skies over Europe in 1944 and 1945 carried more than just bombs and ammunition. They carried the hopes of the crews who flew them, and the nations they represented. And they carried, in their turbocharged engines and carefully maintained systems, the accumulated knowledge of people like Jimmy Donovan, people whose names we may never know, but whose contributions were nonetheless real and significant. When we look back at the air war over Europe, let's remember not just the missions and the battles, but also the maintenance crews working through the night. Let's remember the crew chiefs who listened to their aircraft and understood them in ways that went beyond the technical manuals. Let's remember the unglamorous work that made the dramatic missions possible. And let's remember that sometimes the most important contributions are the ones that are easiest to forget. Jimmy Donovan never sought recognition for his work. He did his job, served his country, and came home to live a quiet life. But his story deserves to be told, not because he was unique, but precisely because he wasn't. He represents thousands of similar stories, most of which will never be told, of people who made a difference in small but significant ways. In remembering his forgotten trick, we remember them all, and we honor their service in the best way possible by ensuring that their contributions are not entirely lost to history. The 4 Wright Cyclones that powered Lucky Strike through 35 combat missions have long since been silenced. The turbochargers that Jimmy Donovan so carefully maintained are rusted and inactive, if they exist at all. The men who flew the missions and the men who maintained the aircraft have nearly all passed on. But the story remains, preserved now in words, a reminder of what dedication and skill and careful observation can accomplish, and a tribute to all those whose service was essential but whose names history has forgotten.